So here the question asks us to prove that the question given some sequence, actually this sequence of functions. So let us read the question first. Consider the complex vector space given in this set. Actually this is the function space, continuous function space on the closed bounded interval 0 to 1. So define on this interval 0 to 1 again. Let fn be the sequence in this set defined by fnx equal x to the power n. So here the dependent variable, or rather independent functions, all functions depends on n, and with n function varies for all x in close bounded interval 0 to 1. So we are asked to that this sequence is converges to 0 in this normed vector space with respect, this is the integral norm with respect to the integral norm. That's the first part, and the second part we are asked to prove the same thing with respect to the sup norm. Okay, first of all, so that's the question. So first of all we have to pick arbitrary epsilon value, because we are trying to attack this problem by typical epsilon and definition. So here we first pick arbitrary epsilon value, then we consider the difference between nth term of the sequence and the given limit, which is 0. Actually this is not the real number 0, this is the map 0. So here we are considering the function space, so each element is a function. So even though it is a sequence, the sequence consists with elements which are functions. Okay, now we are considering the difference. Here we can't use the absolute value because these are not real numbers, these are functions. So we are working on the function space with respect to the integral now. So basically integral is the kind of a generalized version of the length of the vector, so we can use that to describe the distance between two vectors as well, because it is induce the matrix spaces. So here by the definition of integral norm, we have this absolute value, whatever inside this comes to the this with x value with respect to the x. So here just 0 is a 0 map basically. So we get this one, then we substitute what we were given, and x to the power n, we no need of absolute value there because it's already positive, because n is positive and x goes 0 to 1. Then we just Riemann integrate this one, Riemann integrable. So we integrate this one and come up with this one. Here we can some can put directly epsilon here, so that so that we can directly bring epsilon into the picture here, but I go further step ahead and put n here, because n plus 1 is always greater than capital simple n, and the reciprocal of it should be definitely greater than. So now we are bringing the epsilon into the picture. This happens whenever this fraction is less than epsilon. When we subject the simple n, we have this one. So easily by the Archimedean property we can choose this one such that any integer which is greater than this 1 over epsilon value, then then we end up with this one. So that's the first part of the proof, and here we are trying to prove the second part, which is